The idea for today's talk is to expand a little bit on what I covered on the Casper stand-up last week, or this week, I guess. So I want to, recover some old ground because there are people here that weren't there, but then go beyond that. And in particular, part of what I'll be doing is in real time showing you how to run the OSLF algorithm for the justification structures so that you can see how I will develop the judgment notation for both term and type level information. So hopefully all that will make sense as we go into it. Let me share the screen. I'm in the process of preparing a draft. This will be very far from the final draft because I will LaTeX it all up. But first I wanted to just quickly get some notes down rather than, mess about with LaTeX, which often eats up a lot of time just trying to get things on the right place on the page. So the draft has a working title of Casper correctly. One of the points that I bring out in the draft is that the justification pointers do all the heavy lifting in CVC Casper, and justification pointers come to us from the Highland-Ong game semantics for linear logic. So if you're interested in the background, I heartily recommend Highland and Ong's papers on game semantics for linear logic. And they are effectively using justification pointers in much the same way we are. It allows them to enforce single-threadedness and other kinds of things. So they were doing it entirely in a theoretical framework, right? So they were just trying to reason about linear logic. And to the best of my knowledge, they had no intention or idea that this might actually be used in production software to ensure network security properties. But when I was first working out the messaging protocol for Special K, it occurred to me that I could in fact do that. And if you go to the Special K repo, you can see the original code. So I wrote some extremely high level code, high level in the sense that it's very, very abstract. So there's I use a lot of parametric types that gives a framework for defining messaging protocols that have justification pointers. So that's kind of the background where the justification pointers came from. I will point out that it was Vlad who observed that we could use the justification pointers to detect equivocation. So that was his contribution. But the main thing is that the technology that we're building on, it has a solid basis, lots of peer-reviewed papers, and not just pulling some ideas out of thin air. These ideas were have a good long history. They go back about 30 years or so. So that's hopefully people find that background useful and interesting. What I want to do is remind people, well, introduce for people who weren't at the Casper session and remind people who were, that we can take diagrams like this and turn them into a notation that that looks like this. So let me just expand this a little bit. So diagrams that look like this, we can express using a compact algebraic notation that looks like this. So let me go through what the meaning is. So here, what we have is a validators, a graph of the block production of validators, with time advancing in the vertical axis, right? We have validators A through E, and then the lines, the arrows, represent justification pointers. And the black, the heavy border on blocks represents blocks that have been finalized. We can, using that idea, we can define a notion of height for a given block for a given validator. So in particular, if we call this height 1, or well, actually for purposes to make something simple, I will call this height 0. So when a block gets finalized, then we've got kind of a sliding window, right? So the finalization fringe can be thought of as a kind of sliding window, so the height ground gets reset. But from height 0, we can call this one height 1, and height 2, height 3. And that can be defined recursively, so that you can walk downward from the tip of the graph to the last finalized block that a given validator has produced. So I'll stop here before we move on and just make sure that everyone understands the diagrams. Any questions about the diagrams? Okay, good. I'm glad that's all clear. So then the justification notation. So I'm gonna use the one that is slightly more formal, is written this way. So we have a turnstile, and to the left of the turnstile, we're going to introduce the validator identity at a minimum. We'll eventually enrich that, but this is the validator identity. So you could think of this as the address that is used, the public address of the validator. We have a height, which we discussed in terms of this recursive definition to the last finalized block produced by V. And then we have justifications. So these justifications are in fact just pointers to block expressions like this. So you could think of them as hashes for an expression like this. So this will uniquely determine a given block. Any questions about that, the notation? Is this all clear?
Yeah, so far so good.
Okay, so then we have just to reiterate what we said about the height. If Fi is the last finalized block, produced by V, then the block that's immediately on top of that one would be written this way. So Fi will obviously be in the justification for the block on top of it, as well as whatever other blocks V has received and used to justify the production of this block. And then if we set B equal to that block, then we would have V. So we want an informal reading of the turnstile is thinks that. So we would have V thinks that, or another one would be produces. V produces this block at height 2 with these justifications. Similarly, we can count backwards, as I mentioned before. So you can define a little recursive function on this format to get back to the finalized state. And as long as the finalized block produced by V is clearly delineated as finalized, this will terminate. Okay. So before we go on, I'm just going to go pull my tea bags out of my teacup, and I'll be right back. All right, thank you for your patience. Just wanted to get a little Tulsi, Moringa, and Ashwagandha in my system. Okay. So notice that if we have a pair of block expressions, we can combine them. So given two of them, we can combine them like this, and we use this funny tensor symbol to indicate that there isn't a single validator that is producing these two blocks, but rather the pair. And it is important to note that if we reverse this order on the left of the turnstile, we would have to reverse the order on the right of the turnstile. And we can formalize this into a rule. Oh, interesting. Hang on a second. I thought I'd fix this. So given two like this, we can form a judgment like this. I'm just gonna, I was certain that I had, well, that's interesting. There we go. I was certain that I had done this edit. Just want to make this edit real quick. There we go. Very strange. There we go. So any questions about this rule? What it means, or why we might want to use a rule like this? The importance of these kinds of rules is that they allow us to do two things. One is to describe partial diagrams. So now we have expressions that are not just about a single block or a single line of blocks, but in fact about some local view of the network. So again, you'll note sort of how much space this takes up to have a legible diagram versus literally how much space an expression like this takes up. We can quickly type this up. I've been careful to use predominantly ASCII characters. You could replace this with a star if you wanted to, and then it would be all ASCII characters. So you can type it or you can write it out by hand. And for a network of invalidators, we can describe the entire view of the network. We can also use the notation to describe when a validator, say VI, becomes aware of the state of the network. So here's an example. If this is the state of the network, notice that no one validator has this information currently, right? There isn't a, this describes a state which is not available or in the view of any given particular validator. This is God's eye information, so to speak. This it is one example among many where validator VI is aware of the state of this network. So each of these blocks now becomes justifications in a higher level block for VI. Right. So at that point, VI has a view of this state of the network. Once we add stake information to these statements, we can also say when there's enough weight behind a particular state of the network to know that that is that state will never be rolled back. All right, before I move on, let me check and see, are there any questions? Is this all clear?
Yeah, I do have one question regarding the choice of the tensor. I guess my original understanding of tensor was, it was something that imposes some type of restrictions or limitations on something else. But here it's more of identifying validator as separate and unique or distinct from one another. Are we having a sort of a new or different interpretation of what a tensor is, or is it still in line with this idea of restricting and limiting?
It's still in line. For linear logic, tensor constrains the formulae to be isolated with respect to resources.
Okay, so each validator is isolated, so it falls within that understanding or definition of what.
In particular, these two blocks are separate. They're separate blocks.
Okay, so not so much the validators, which are separate, it's more the each individual block that an independent validator is.
Again, what we're describing is a pair of relationships, right? So here's a relationship and here's a relationship. And over here, we're sort of indicating that there isn't too much interaction. So we can think of these as independent validators. They're not entangled, so to speak.
Mm-hmm.
And they have produced two independent blocks.
Okay, understood.
Yeah.
I had a question on the validator's block finality. If you want to go back up to the diagram.
Mm-hmm.
If I get this correct, that final row of blocks are the ones that are diagrammed in a black outlining that represents their finalized. Does that mean the blocks above are unfinalized blocks?
That's correct. Right. So these blocks have been finalized, but more blocks are being produced on top of them. So the finalization fringe, which this row represents, is always lagging behind the block production. So at the beginning of the network, this is Genesis, right? These all come down to one block, which is Genesis. and then all the blocks above refer to Genesis, right? And then eventually you'll get a row of blocks like this one, which is above Genesis, but nobody's ever going to roll them back. So that becomes the next finalization fringe. And once we have a, go ahead.
Well, going into some work that's particular to RChain, block merging, when transactions in a block, non-metadata transactions in a block are validated by block merging, those don't trace back to the Genesis block, correct?
They trace back to the last finalized state, and that's what I was about to say. So if we think about it, we start at Genesis. That's the only block, and that represents the finalized fringe. Then we build a bunch of blocks on top of Genesis, and we ultimately get a row of blocks that are also all finalized. And so we can forget about Genesis and only go from this point on. And so this is what I was saying. It's a kind of sliding window. Does that make sense?
Yeah, that clarifies.
Cool. All right. As I was saying, there are other ways for VI to become aware of a state like this. So you could imagine that at height h+1, this block is missing two justifications, right? So we have k and hk+1 are not present in this justification. And so then at some later height, say hi plus j, it gets the k and k+1 somewhere in here. Then at that point, this would be a block that at which we could conclude that the VI sees the state of the network here. So the point of that is just to say that it doesn't have to be the case that VI sees all of these blocks at the very next level. It could be much higher in the graph before it has enough information to see this network state. So now I want to take a brief digression. For those people who are unfamiliar with the justification or judgment style notation for in programming language semantics and logic. And it's going to become important later because what we're going to do is utilize some intuitions here to upgrade this notation. So here's a spoiler. This notation currently is only at the term level. There's no type level information. So this is describing, if we think of blocks as terms, this is describing valid blocks. So the production of valid blocks. Not just for individual validators, but for the entire network. And in particular, rules of this type show us, how we can go from individual valid blocks to network, a network producing collections of blocks, and then how those collections get re-internalized into individual blocks. So that's kind of a term level validity. So over here, I've color coded this rule, and notice that this rule is very similar in shape to a rule like this. So we've got a judgment and of a particular shape, and we're going to produce a new judgment of a slightly different shape that uses the information. The key difference between this rule and say this rule here is that there are two judgments being used to form a single judgment here, whereas there's only one judgment being used to form a judgment below. But typically these rules are of the form in judgments on top, a single judgment at the bottom. So you could think of it as a function, an in-array function, which takes in inputs, each of which are judgments, and produces a new judgment. So in this sense, what it really is, at least rules of this kind are can be thought of as constructors. Right? So we're taking some data in, which is going to be input to constructing a particular judgment. The one that we've got in front of us is fairly typical of the judgment for a well-typed lambda abstraction. So if you're not familiar with the judgments of this form, to the left of the turnstile, what we have are type contexts, and these are effectively lists. They are lists of pairs assigning variables types. So inside gamma, you'll find some other variables and types. So this is saying that, you know, there's some prefix, which is a list of variables and their types, and the last element in the list is the pair xt, and the idea is that we're making an assumption that x is given type t. So using these assumptions, we can establish that the term e, so this is some lambda term, the term e is of type u. So given this judgment, where we have x sort of called out in this typing context, we can get rid of x from the typing context, and we're going to put it into the lambda abstraction, so it becomes the formal argument to this lambda expression, lambda x dot e, and that type is going to be give me a t. So this t is governing this x. If you give me a t, I can produce a u. So right. So essentially, this is just a restatement of what this says. If I know that x is of type t, I can produce an e of type u. So that's tantamount to being able to form a lambda abstraction. If I know that x is of type t and you've given it to me, then I can produce an e of type u. So that's sort of standard fare for the formation of well-typed lambda terms. And the reason I've color coded it is that there are really two judgments. One has to do with well-formed lambda terms, and the other has to do with the formation of logical formulae. So if I was able to establish these formulae over here, and given these formulae, I could conclude U, then I can conclude that T implies U. So this rule here is really can be thought of as a manifestation of the Curry-Howard isomorphism. So it's effectively correlating logical formulae to types, and it is correlating terms, program terms, to proofs. So this term is a witness for this particular formula. So that's how Curry-Howard is manifesting in this rule for constructing judgments. Any questions about this? It's all bread and butter if you've seen this stuff before, but if you haven't seen it before, it might be a little confusing. So hopefully everyone is comfortable with this notation. So now we can see that our notation up here is missing type information. And so what we're going to do is we're going to expand this notation to provide type information. And we're going to provide type information on both sides, right? So if we think of these as like variables, even though the variables are not mentioned here, what the variables are really going to stand in for, or we're going to replace them not with variables, sorry, we're going to replace the variables with programs. So these programs become Rolang terms, and we're going to give them we're going to assign to these Rolang terms some behavioral types. I would like to be able to make this talk self-contained, but that would take us well past the hour I've allotted for the talk. So the reference for that would be the row calculus paper and the namespace logic paper. So you can look at the namespace logic. So that logic will be given, will be used to assign types to the Rolang terms that are standing in for our validators. And now it should be understood that I ran a primitive version of the operational semantics in logical form algorithm to generate the namespace logic. So that logic was algorithmically generated from the row calculus specification. If you are interested in the details of that algorithm, there is a form of the algorithm that Christian Williams and Mike Stay codified in a paper that they produced last year about this time. Now that algorithm does not do certain things, but for the purposes of this talk and for entry-level understanding, that algorithm is sufficient. That description of the algorithm is sufficient. So it covers an extremely wide class of examples. So for any model of computation that has binders, so lambda calculus, row calculus, yada, 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 they can produce a set-based logic or a topos theoretic logic that has operators for that correspond to the semantics of namespace logic or things like namespace logic. So again, I would love to be able to go into those details, but I can't do it in 20 minutes and still cover the whole point. So I want people to get a kind of end-to-end description. So what kind of things are we looking at? So the validators, when expressed as Rolang terms, will have a shape that looks roughly like this. Okay, so the shape is a validator V is going to, let me slightly modify this notation. Let me do it this way. And I'll move it over here. So we'll get V S. So this is the identity for this validator. So it is the place where it is listening to receive information from other validators. So that's the channel there. And S is the state. So this is its view of the state of the network. So the blocks that it needs to remember that it has produced, along with any information regarding transactions. So basically a copy of the tuple space. So that's what we can keep inside S. And then these are the addresses of the rest of the validators, right? So V1 through Vn. So if they're n validators, this is n minus 1. So these are all the other validators. All right, so we have n plus 1 total channels that the V program is parametric in. And then what this validator will do is it will listen on its, so let me call this V instead of VI now. So it will listen on its name for any blocks produced by the validators sitting at these, right? So remember, we're going to have a network of programs like this, and essentially the arguments are going to be permutations of this argument list, except that the S's will all be fresh. They'll all be distinct from each other. So it picks up any block that has been sent its way. It goes and grabs its state, which tells it what height it's at. So this is a memoized version of the height. And the blocks that it has received in the past. And then it produces a new block, which is going to be the height plus 1. Together with the block list as justifications, right? So this comma here is sort of Lisp style notation for splicing this list into this set here. And then it will publish the next block out to all the other. This should be n minus 1. It will publish this block out to all the others, and then go back to being itself with the updated version of the state. Okay, so that's a quick sketch of the kind of Rolang term that would describe a validator. Any questions about that? I mean, obviously it will be more complex than this, but I'm just sketching it out so that people can get a sense of how you might do that in Rolang.
The list notation confuses me.
Oh, you mean here?
Yeah.
Well, this is going to be a list, but I don't want to build the set, which the single element of which is a list. I want to take each of the elements of this and put them into this set. And that's what this does.
All right.
Okay. Any other questions? Okay. So if you go and look at the namespace logic paper, you will you'll see what kind of types you can generate using namespace logic, and those types would be the kind of types that we could associate with an expression like this. So that's the kind of type that we'll put here. And now I want to get to the block types. So let's we'll do this in real time. We've got 15 minutes, so let's do that. So what we're going to say is that a given block expression, so I'll say B, is of the form. What does it look like? Well, it's going to be a height. And then what's on the inside of this? Well, it's just block expressions, right? So as many block expressions as you might want. Is that clear as a notation? And then you can you can see that since this could be 0, you don't have to have an empty block. If you're more comfortable, you can add a you can add the empty block, which I'll just denote. What's a good? I'll denote it this way. So you could have it that way if you wanted to, but it's not required for this grammar to be well-founded. Any questions about this as the grammar for block expressions? Any programmers in the audience should be able to see how to turn this into a Scala data type or a Java data type or a JavaScript data type. This is clear?
Yep, sounds good.
Okay, all right. So the logic that we would generate would be of the form, so since we're only going to be interested, at least in this talk, in set-based logics, we'll get true, the negation of a formula, and the conjunction of a formula. And just for grins, I'm going to use 2 variable heads. Oops. That way I can distinguish here. Okay, that part of the formula should be bread and butter if you're a programmer or computer scientist or mathematician. Make sure I haven't got that on. Okay, and now comes the interesting bit. I'll do this in stages. We can put an H here, and then we can put as many fees as we want. So that will now describe blocks where you have specific height numbers. But suppose you wanted to have a height, not a specific height, but a height predicate. So then we would do a similar kind of thing for arithmetic. I'm not going to go through it here, but we would do a similar kind of thing for arithmetic, and then put here, instead of a particular height, a property which would pick out sets of numbers, right? So I'm going to replace h with, let's say, iota. Okay. So this is now not a given number, but a predicate, which you could apply to numbers. So an example of such a predicate would be is prime. So you could check to see if the height is prime. And if the height is prime, then you check to see that the justifications each satisfy these specifications. And again, we would, there's an order here, so there would be an order here. So that means that it's not really a set. We're really thinking of it as a list in order to do this kind of logic and make it simple enough to describe in 15 minutes. So that's our logic for our type specification for blocks of this kind. Any questions about that?
The hopefully I'm trying to formulate my question. I know what I say. I know what I want to say, but I'm not sure how to say it. So iota, or this height, it's as if we're creating a range of height. So if blocks are produced within this range, X happens. If it's outside of this range, then Y happens. Is that how to think of this?
Something like that. It's literally just a logical specification that we will check against the height number for a given block. So the logical specification could be even, right?
Mm-hmm.
So it could be the predicate is even. And then we would check and see if the height A is actually even.
Okay, gotcha.
Okay, so now we can formulate typed judgments. Okay, so now our judgments are going to be of the form. So I've got, oops, that should be this one. All right, so, and then I'll have this, hang on a second. So let's see how best to do this. This is going to be a different index. Oh, I see how to do it. Okay. Okay. Oops. Okay, so this is what's showing up on the left hand of the turnstile. So we're insisting that these are the validator expressions, that they have these types. And now we're going to give we're going to give blocks like this, and they're going to be of given types. Okay, and so then we're going to have formulae of the form phi, and this will be 1. And here. Oops. Oops. Like that. So a particular network will be a particular state of a network that corresponds, that enjoys certain properties, T1 through Tn, together with phi1 through phi(n), will be written in this way. So maybe I will put this on 2 lines just so it's a little easier to read. Hopefully that's clear. Does that make sense? Are people able to read this?
I can follow it. I'm, you know, I'm almost there, but
Okay. All right. So it's just an extension of this kind of notation in the using the kind of thing that we're doing here. Okay, so here we've got some stuff on the left that we're also decorating with type information. And we've got stuff on the right that we're also decorating with type information. And so here, the stuff on the left is being decorated with type information, right? And the stuff on the right is being decorated with type information. So the blocks are decorated with type information. And well, we're out of time, but here's the shape of what's going to happen. We will describe a set of rules like this rule here, such that you can only build networks that have the properties. And so those properties are going to be expressed here and here, that that no validator equivocates, or if it does equivocate, then it is eliminated from the network. All validators are live, right? So you don't get deadlocks in the validators, and you don't get other kinds of constrained liveness considerations. And we will be able to prove that the well-typed networks have those properties, right? So if you follow the rules for how you build the networks, then the networks will only ever generate good DAGs, where the DAGs have, you know, the layered finalization fringes, and there's no equivocation, et cetera, et cetera. That's how the proof will go. Does that make sense? What?
Makes sense to me. I note that in HN with the collection of blocks JN through JNN.
Yeah.
That notation implies that all blocks have the same type phi n. Or
No. This is a phi1 is governing this one, and phi n is governing that one.
right. So at the end, at the very end of the expression, HN, JN1 to JNN.
Yeah.
Colon phi n. So all blocks JN1 through JNN.
No. Notice that phi has inner phis. Right.
Yeah.
So the inner phis will govern the J's.
Okay.
I mean, you could do something as simple like, put a true inside here,
Yeah.
right? Which doesn't constrain these at all, as an example. And this framework is what gives CBC Casper correct, but the CBC part of it, why it is in fact correct by construction. There has been a misunderstanding about what correct by construction means in the community that Vlad built up, because there just wasn't enough time to help all of those folks understand what CBC means. So in the case of the lambda term, these rules will only build up correct lambda terms in the sense that they are well typed. And the terms that are all well typed will have a particular property. So typically the property that you get with the type system F is that the term normalizes. The normalization stops, right? So as you're reducing the term, you'll eventually get down to something that you can't reduce anymore. But you won't get into an endless loop like, lambda x dot x applied to lambda x dot x, right? That will be eliminated by the type system. You can't make that term, right? And so in that sense, the programs that are built by the typed judgments are correct by construction. Similarly, the networks that we build using the rules will be correct by construction. As long as you build your shards using the rules, they will have the Casper properties. Right? So that's what's meant by correct by construction. And now this gives us a framework in which to write down the network construction rules and to prove that all the networks that are built using those rules have those properties. So I need to leave it there, but any final questions or comments?
Looks good.
Cool. Thank you. Yeah, a little Christmas gift to the community. So we now have, yeah, we now have the framework in which to do all of the formal stuff, and it follows nicely on the heels of the specification of the interaction between block merge and finalization. So maybe I earned my pay for the week.
There you go.
All right, folks, thank you so much for your time and attention. I appreciate it. And please have a happy new year. Stay safe, stay warm, and we'll see you on the other side.
Thank you. Happy New Year to everyone.